Hey everyone, Mr. Hauk here. In today's video, we're going to be looking at the graph of the parent function for tangent, and we're also going to be looking at some characteristics of different trig functions. Let's go ahead and get started. So here on your notes, notice that we have the angles 0 to 360 degrees, and I've gone ahead and filled in the columns for the angle in radians and for the tangent of those angles. What we want to do is we want to take this graph and we want to go ahead and graph it on the plane provided. So let's go ahead and plot some of these points and graph it. So I can see that we have the point 0, 0. We have pi over 6, comma, square root of 3 over 3, which is going to be kind of hard to estimate. We have pi over 4 and 1, which again, these points are kind of hard to estimate. But we can see that we have undefined tangent values at pi over 2 and 3 pi over 2. So what that means is we have some asymptotes. So I'm going to go ahead and draw in some asymptotes here. Okay, these are the points where the tangent is undefined. So pi over 2 and at 3 pi over 2. So if we were to go ahead and graph the other values, well, let's try to estimate some of these. So we have pi over 4 and comma 1, and let's just go ahead and say that maybe this will be 1, or let's make this 1. This can be negative 1. So pi over 4, that'd be about right here, and we would end up with a curve that kind of moves like that. Similar, if we have 5 pi over 4 comma 1, well, 5 pi over 4 comma 1 would be about there, and then 3 pi over 4 comma negative 1 would be about right there. So we would have, oh, that looks terrible. Let's try that again. It looks a little something like that. And then we'd also have 7 pi over 4 comma negative 1, so that would be about right here. And that part of the function would look like that. So tangent is very different looking from sine and cosine. Let's go ahead and talk about the domain of y equals tangent of x, the parent graph, or the parent function for tangent. So for our graph here, we know that pi over 2 and 3 pi over 2, we have undefined tangent values. And we also know that if we continue to add pi, so pi over 2 plus pi gives us 3 pi over 2. If we added pi again, we'd get 5 pi over 2, and that would be undefined. If we added pi again, we'd get 7 pi over 2. So it's looking like odd multiples of pi over 2 are giving us problems in the domain, but we have everywhere else in the domain is fair game. So what we would say is the domain for tangent is all real numbers except odd multiples of pi over 2. And again, that would be things like pi over 2, 3 pi over 2, 5 pi over 2, on and on and on. Okay, now let's talk about the range. Well, notice that for the y equals tangent of x, the range is actually all real numbers. So we'd say all real numbers. That's the symbol for all real numbers in case you didn't know. We could also write that as negative infinity is less than y, less than infinity. Okay. And the third question here is, does the graph of the parent tangent function have any symmetry? Well, it actually does have some symmetry. It's very similar to when we looked at the sine function. We saw that the sine function had odd symmetry. The tangent function also has odd symmetry, and we can see this by looking at a graph of tangent on Desmos. So let's go ahead and pull up a graph here. I'm going to change my steps to be in terms of pi over 2. We're already set to radians, so that's good. Let's go ahead and graph y equals tangent of x. And we can see here, remember that odd symmetry is when we take a point and we have a reflection across the origin to get another point on the function. So let's say if I took this point right here and I reflected it across the origin, we'd get over here. And we can see that every point on the function of y equals tangent of x has origin symmetry, therefore we have an odd function. So let's go ahead and record that. So tangent has origin symmetry, which means we have an odd function. Okay, so far in the previous video we talked about cosine having y-axis symmetry, so cosine is an even function. We saw that sine has origin symmetry, so sine is an odd function. And now we can see that tangent also has origin symmetry, so tangent is also an odd function, similar to sine. Okay, well, one of the things that we need to talk about with trig functions is something called the period. So we call a trig function that repeats a pattern at regular intervals a periodic function. So as we saw in the previous video, sine and cosine are periodic functions, and as we just saw with tangent, tangent is also a periodic function because those functions repeat patterns at regular intervals. We call one complete rotation of the pattern a cycle, and the horizontal length of a complete cycle we call the period. In sine and cosine functions, we can also think of the period as the distance from peak to peak. But essentially, we're looking for how long is the length of one complete pattern cycle. Okay? So based on these graphs, let's try a couple practice problems. Let's try to identify the period of these three graphs. So starting with the graph here on the left, let's choose we'll go with green here. So with this graph here, we want to figure out how long does it take, or what is the horizontal length of one complete cycle? Well, let's highlight one cycle. Okay, there's one cycle here. We can see that we started at 0, we ended at 8 pi, and the horizontal length here, 0 to 8 pi, would be 8 pi. So the period, and we're going to use capital T to represent period, the period here is 8 pi. Let's try another one. If we look at this middle graph, well, let's go ahead and highlight one complete cycle. So, okay, there's one complete cycle, then the pattern is going to repeat itself. And if I look at peak to peak, here's 0, here is pi, and the horizontal distance here from 0 to pi is just pi. And we can even see the pattern repeated again here. So if I put another point here, we can see from here to here, we have another cycle, another period of pi. So here our period would be t equals pi. All right, now we have what looks to be a version of our tangent graph. So let's see. Let's look for parts that we can see here. I can see a point here at 0, -2. I can see a point here at 2, -2. And it looks like we're going from 0 to pi over 2. So this horizontal distance is distance pi over 2. And that would be the same distance all the way across. So this would be pi over 2, this would be pi over 2, so on and so forth. Okay, so here the period is pi over 2. So that's how we can look at the period when we're looking at a graph. We look for how long what is the horizontal distance, the horizontal length of one complete cycle, and that's the period. So let's see if we can notice a relationship here. On the left, we have the parent function for sine. We have y equals sine of x. And let's go ahead and highlight one full period. So there's one full cycle. So the period from 0 to 2 pi, so this tells us that the period is 2 pi. Now let's look at a transformed version of the parent function. We're going to look at y equals sine of 3x. And let's go ahead and highlight the period or cycle here. So notice that it's a much quicker cycle. The cycle is over by 2 pi over 3. So here we have that our period is 2 pi over 3. Okay. So we want to think, what could have happened here? Let's look at the differences in their equations. Y equals sine of x, y equals 3 sine of x, and simply by multiplying x by 3, we're going from a period of 2 pi to a period of 2 pi over 3. Well, let's see if we can notice the same, maybe a similar pattern happening with cosine. So we have right here, we have our parent function for cosine, y equals cosine of x. Let's go ahead and highlight one full cycle. Okay, so there's a full cycle. Cosine will start to repeat itself after 2 pi. So we can see here that similar to sine, that the period of y equals cosine of x is going to be 2 pi. And now let's go ahead and check what happens when we have y equals cosine of 2/3 x. So let's go ahead and highlight one full cycle right there. And this is, the full cycle goes from 0 to 3 pi. So here our period is 3 pi. And once again, the only thing we changed, we had y equals cosine of x, and now we have y equals cosine 2/3 x. So it seems by going from a 1, this is just a 1x, to a 2/3 x, that changed the period from 2 pi to 3 pi. So let's see if we can notice a relationship here. With y equals sine of x and y equals sine of 3x, it seems like we took the original period, which was 2 pi, and this is a 3, so we took 2 pi, we divided it by 3, we got 2 pi over 3. Let's see if that works here. With y equals cosine of x, the original period was 2 pi, that's the period for the parent function cosine, and I wonder what happens if we take 2 pi and we divide it by 2/3. Well, let's try the math here real quick. So let's try this off to the side. If I take 2 pi, divide it by 2/3, well, that's the same as saying 2 pi over 1 times 3 over 2. And that would equal 6 pi over 2, which would simplify and reduce to 3 pi. So it looks like that does work because that's the period that we got, was 3 pi. So in general, if we have y equals a sine of bx and y equals, or I should say or here, or y equals a cosine of bx, then the period, which is uppercase T, is going to be equal to 2 pi divided by this number b that's being multiplied inside the parentheses to x. Okay, so the period is equal to 2 pi divided by b, and again, b is this coefficient of x inside the parentheses. And notice that we're using 2 pi because that's the original period for sine and cosine. So I wonder if tangent will work out the same. Well, let's investigate. So here's the parent function for tangent. And let's go ahead and notice that for tangent, one cycle will go from 0 to pi, and the horizontal distance, the horizontal length of this cycle is exactly equal to pi, so t equals pi. So the period for tangent is pi instead of 2 pi. Again, notice that sine and cosine had a period of 2 pi for their parent functions. The parent function of tangent, just y equals tangent of x, has a period of just pi. Now let's look at an example here where we have y equals tangent of 4x. Well, if we try to, I might need to zoom in here, but if we went from 0 to pi over 4, because these are where the points are applying, we can see we have a horizontal distance of pi over 4. Okay, so here the period is pi over 4. So let's see if we can notice what changed here. We went from y equals tangent of x, the parent function for tangent, to y equals tangent of 4x, and the period went from pi to pi over 4. So it seems that we are taking the period for the original function, the parent function, which is pi, and dividing it by this coefficient 4, because pi divided by 4 gave us a period of pi over 4. So in general, if we have a tangent function, a tangent of bx, then the period, which equals t again, will be equal to pi, which is the original period for the parent function, divided by whatever that coefficient of x is, which is b in general. So to kind of look at those again, if we're looking at sine and cosine, the period is 2 pi divided by b, where b is that coefficient of x. And for tangent, because the period for the parent function of tangent was just pi, then the period for a tangent function is pi divided by b. Okay, so let's do some practice here. Let's find the period in radians for the following. So the first one says y equals cosine of 2x. So since we have a cosine function, we know that the period is going to be equal to, let's get auto shape recognize off, the period is going to be equal to 2 pi divided by b. Well, we know that b is 2, so we have 2 pi divided by 2, which is just pi. Okay, so there's our period, and if we wanted to, we could graph that in Desmos, and we could see from peak to peak, since that's a cosine function, the horizontal length of one complete cycle would be pi. Okay. Next up, we have y equals 1 plus 2 tangent of x thirds, and since this is a tangent function, we know that the period is going to be equal to pi divided by b. Remember that b is the coefficient of x, and the coefficient of x here is 1/3. Okay, x over 3, that is the coefficient of 1/3. So this would be pi divided by 1/3, which is the same as saying pi over 1 times 3 over 1. Keep change flip. Pi over 1 times 3 over 1, that's just 3 pi. So this function would have a period of 3 pi. Next, let's take a look at y equals 1/2 sine of 1/4 x minus 1. This is a sine function, so we know that the period is going to be 2 pi divided by b. Notice that b is 1/4, so this is going to equal 2 pi divided by 1/4, which is the same as saying 2 pi over 1 times 4 over 1, which is 8 pi. Okay, so this function has a period of 8 pi, repeats the cycle every 8 pi. And then lastly, let's take a look at y equals 4 tangent of 2x minus 2. This is a tangent function, so we know the period is going to be pi over b. b is 2 here, so this is going to be pi over 2. Okay, so pretty easy. When looking at, when given an equation for a trig function, either sine, cosine, or tangent, it is pretty easy to take or find the period. Now we want to talk about something called the midline. So for sine and cosine functions, we call them sinusoidal functions. For sinusoidal functions, the midline is the horizontal center line that the function goes above and below. The midline will always be parallel to the x-axis and is located exactly halfway between the maximum and minimum values of the function's graphs. So let's look here for our first example. I can see that my maximum value is occurring here where the y value is 8, and I can see the minimum value is occurring here where the y value is 0. So that means that halfway between the maximum minimum values, halfway between 8 and 0, would be 4. So I'm going to draw a horizontal line, and the equation of this horizontal line is y equals 4. And let's just verify real quick. Let's make sure that this midline has the same distance from the top, the maximum value, to the bottom, the minimum value. That way it's truly the midline. So from the maximum value, 8, to the midline 4, we can see we have a distance of 4. And from the minimum value down at 0 to the midline, we also have a distance of 4. So y equals 4 is indeed the midline here. Taking a look at another example, we have our maximum value appears right here at -1/2, and our minimum value appears here at -1.5. So if we look halfway between that, we would have a horizontal line at y equals -1. And again, let's just go ahead and verify real quick. From the maximum point to the midline, we have a distance of 1/2. And from the minimum point to the midline, we have a distance of 1/2. So y equals -1 is indeed the midline. Okay, notice that we're only doing midline here for sine and cosine for sinusoidal functions, because tangent, as we saw with the range, has a range of negative to positive infinity, meaning that, you know, if we tried to find a maximum or a minimum, we wouldn't be able to. So midline is not going to apply to tangent functions. All right. So now let's talk about the amplitude. For sinusoidal functions, we call the amplitude half the positive difference between the maximum and minimum values. So it's very similar to what we were just looking at for midline. You know, when we looked at midline, we found the line that was half the distance between the max and minimum. So let's try this here with y equals 5 sine of x plus 1. If I went halfway between the maximum point, which is located up here at 6, and the minimum point, which is located down here at -4, well, that would put me exactly right here. Okay, so the midline looks like it's at y equals 1. If we look at the difference, so if we look at the distance from the midline to the maximum point, well, from 1 to 6, that's a distance of 5. And if we look from -4 to 1, again, that's going to be a distance of 5. And that distance from either the maximum or the minimum to the midline, we call that the amplitude. So here, our amplitude is equal to 5. I'm just going to use amp for short for amplitude. So my amplitude is equal to 5. Now, can we notice a relationship between the amplitude and the equation? So the amplitude was 5, and notice that the coefficient of sine was also 5. So I'm going to put the relationship was the amplitude is the coefficient of sine. Okay, well, let's see about this next problem. So we have a maximum value up here of 4, minimum value down at -4. That means that 0 would be the midline here. And again, let's just double check. This distance from max to the midline, that has a vertical distance of 4. The distance from the midline to the minimum value has a vertical distance of 4. So we would say that the amplitude is equal to 4. Okay. Now notice, though, that for this equation, y equals -4 cosine of 2x, the amplitude and the coefficient of cosine have different signs. So I'm going to say that the amplitude is the positive coefficient of cosine, or the absolute value of the coefficient of cosine. So the amplitude is the absolute value of the coefficient of cosine. Okay. So it actually turns out that in general, for sinusoidal functions, sine and cosine functions, that the amplitude is actually this coefficient A, the absolute value of that coefficient A. So let's try a couple practice problems. They won't take but a minute. We want to find the amplitude for y equals -7 cosine of 2x. Well, we know that A is equal to -7, so the amplitude will be equal to the absolute value of -7, which is just +7. Okay, if we look at the next one, find the amplitude of y equals 5/2 sine of x. Well, we can see that 5/2 is the a value, the coefficient of sine, so we take the absolute value of 5/2, and we still just get 5/2. Okay, and then lastly, we notice that we did not discuss amplitude with tangent functions. Why wouldn't we discuss amplitude, or why does amplitude not apply to tangent functions? Well, it's very similar to when we just talked about midline. We don't have a maximum or a minimum distance, or we don't have a maximum or a minimum because we have our ranges from -infinity to infinity. So since tangent functions don't have max or mins, we have no amplitude. So it's because tangent functions don't have max or mins. Ooh, shape recognition, go away. There we go. Tangent functions don't have max or mins.